Hello everyone, this is Shentong. Today I would like to share our work representation disentanglement in generative models with contrastive learning. So here our presentation lines. The first part is the problem setup and the motivation. So here are preliminaries for the methods to do disentanglement of factors in imager. So there were three main pipelines. The first pipeline used adversarial frameworks with min-max optimization. The second pipeline applied non-adversarial frameworks with variation other encoders. So recently, the third pipeline became popular with using the semi-supervised methods. So the first method is called LORD, that used latent optimization with a noise regularizer. And the second method is called overload, that disentangled class correlated and uncorrelated attributes. However, there were two main limitations behind those works. The first limitation is that using separate encoders for different factors is resource wasteful for real-world applications and requires expensive human design. And the second limitation is that learning only the content embeddings inside each sample is not sufficient to learn the diversity in dataset. So in this work, we present the ContraLORD, a simple but effective method that incorporates contrastive learning into latent optimization for disentanglement. So our ContraLORD is mainly composed of two parts: embedding optimization, encoder pre-training. For embedding optimization, we use a generator to learn discriminative and disentangled embeddings with latent optimization. For encoder pre-training, we apply an encoder and a momentum encoder to dynamically learn disentangled information across larger amounts of samples with content and residual-level contrastive loss. So for content-level contrastive loss, we want to learn more disentangled content embeddings across examples in a content momentum queue. For residual-level contrastive loss, we want to further disentangle the residue part in embeddings from the residue momentum queue. So here is the overall objective and the algorithm for our method. So we also measure the smoothness of embeddings pre-trained by our ContraLORD. So in the experiments, we compare our method with previous baselines and the state-of-the-art methods. So for linear classification, disentanglement results on synthetic and real dataset, we achieve the best performance in terms of most metrics. So for application study, we explore the rationality of each loss in our ContraLORD, and we also explore the importance of the batch size and the lective samples in disentanglement. So overall, in summary, we present ContraLORD, a simple but effective framework for representation disentanglement. And we also formally explore the disentangled features across many samples with content and residual level contrastive loss. And the extensive experiments on synthetic and real dataset also show the effectiveness of our approach to learn the disentangled representations. So that's all. Thank you.